Hello everyone and welcome to today's webinar. On behalf of American Petroleum Professionals of Iranian Heritage, APPIH, it's our great honor to start another webinar on the subject of scale inhibitors retention in carbonate reservoirs during squeeze treatment by Mr. Khosro Jarrahian. He joined us today from the UK. Mr. Jarrahian works in the flow assurance and scale team FAST at the Heriot-Watt University of Scotland. His research interests include surface chemistry applied in the petroleum engineering, particularly the effect of surfactant absorption on the wettability of reservoir rock, mechanistic studies of scale inhibitors, retention of by examining static adsorption, compatibility of scale inhibitors. He also works in the Priemer Corex company as a formation damage expert. I would like to thank Mr. Jarrahian for accepting our invitation, and without further delay, I'm transferring microphone to him for starting his presentation. Thank you.
Thank you very much for Hamid Reza for brief introduction. I am Khosro Jarrahian from Priemer Oilfield Group. Today, I am going through scale inhibitor retention in carbonates during squeeze treatment. First of all, I'll go through definition of scales, mechanisms of scale formation, mechanism of scale inhibitor retention, scale inhibitors, and experimental section includes static adsorption theory, experimental results, and the presentation comes to end with summary and conclusions. So first of all, we need to understand what scale means. What's the definition of scale? As you probably know, scale or inorganic scale accurately is any crystalline deposit salt resulting from the precipitation of mineral compounds present in water. And this kind of scale typically precipitate out with one or more types of inorganic deposit along with other debris, such as organic precipitates like asphaltene, wax, sand, corrosion products, etc. So what's the main mechanisms of scale formation? As you can see in the first one, so carbonate scales precipitates due to changes in pressure and temperature around the wellbore. And this kind of scale forms around the wellbore and production facilities. So as you can see in the reactions, we have a stream of water coming from reservoir into the wellbore. Around the wellbore, due to pressure differentiates, some CO2 is evolved from the water stream and the pH of solution is increased. As a result, calcium carbonate scale is formed around the wellbore. Another type of scales, which is very hard to remove, is sulfate scales. And it forms due to mixing of incompatible brines. So imagine that you have an oil reservoir and because of maintain the pressure of the reservoir, you need to do water flooding. So in water flooding, you have seawater as an injected water and formation water, which has already existed in the formation. So seawater is a rich source of sulfate. On the other hand, formation has particularly divalent calcium like divalent cations like barium, strontium, and calcium. And due to mixing of these incompatible brines, these ion and cations contact together, react together, and sulfate scale forms. And the last type of scales is halide scales, and it is formed due to dehydration. It also forms around wellbore and production facilities like carbonate scales. Now, we need to prevent scale formation around the wellbore. One of the most economical and common methods in the oil industry is scale inhibitor squeeze treatment. As you can see in the figure, it comprises of 5 stages: pre-flush, main treatment, overflush, shut-in, and back production. In pre-flush, we need to inject mutual solvent or any type of surfactant to prepare the surface of rock for retention or absorption of scale inhibitors on. And the main treatment includes injection of squeeze of scale inhibitor through the production line into around the wellbore. And after that, we need scale inhibitors to reach the deepest part of reservoirs, or in reservoir. In this case, seawater is used as an overflush agent. After that, the well is shut in for 24 or 48 hours to let all scale inhibitor injected retained around the wellbore. And after this period of time, the well is brought back to production. In back production stage, the all adsorbed scale inhibitors or precipitated, in some cases, are adsorbed from the surface or redissolved in water stream and prevent the reaction between anions and cations. So let me give you a brief introduction what the scale inhibitors. Scale inhibitors are weak polyacids, and they will be dissociated as pH is increased. So more pH, higher pH, more dissociated scale inhibitors. As you can see in the figure, as pH is increased, the amount of dissociation of scale inhibitor is also increased. And if scale inhibitor is dissociated, it can interact with divalent cations like magnesium, strontium, barium, or particularly calcium, and it can be precipitate out. So as a brief introduction for precipitation of scale inhibitors with divalent cations, we need 2 parameters: higher pH and higher concentration of divalent cations, particularly calcium. So now we need to understand what the main mechanism of scale inhibitor retention is. There are 2 different types of retention mechanism: adsorption and precipitation. In adsorption mechanism, the scale inhibitor, the dissociated scale inhibitor, is adsorbed on the surface of rock through electrostatic interaction or physical interaction between the rock and mineral formation. On the other hand, in precipitation, the scale inhibitor interacts with divalent cations, particularly calcium, and get precipitate. So now the question is how we can distinguish adsorption and precipitation. The answer is here. If apparent adsorption results are plotted versus final scale inhibitor concentration, and the results are plotted for 2 different types, for 2 different mass volume ratios, as long as the results for 2 mass volume ratios are moving along adsorption isotherm, pure adsorption mechanism is dominantly occurring. However, after a specific concentration, the lines starts to deviate from adsorption isotherm. It means that the retention mechanism is changing to couple adsorption and precipitation. And by this formula, we can calculate how much scale inhibitor has been retained on the process media, which V is volume of scale inhibitor solution, and this is the difference between initial and final scale inhibitor concentration divided by mass of substrate. So now I am going to present all experimental results which I have generated during my PhD. As you can see, I have done a comprehensive study of scale inhibitor retention mechanisms on carbonates. And today I am going through just two important scale inhibitors, DETPMP and PPCA, which are widely used in oil field. Now the experimental section, the test condition for DETPMP are as follows. The scale inhibitor concentration varies from 0 to 4,000 ppm. Mass of substrate is 5 and 10 gram calcite and dolomite crushed. The size fraction is 100 to 315 micron. Temperature is a reservoir-like temperature, 95 centigrade degree. pH has been adjusted 4 and 6, and the brine matrix is North Sea water. So here I am going to show apparent adsorption result versus final scale inhibitor concentration. As you can see, in both cases, calcite dolomite at pH 6 and pH 4, from 0 to 100, we have pure adsorption mechanism. And above 100 ppm, the lines start to deviate from static adsorption, which means, as I already mentioned, the retention mechanism is changing to couple adsorption and precipitation. And interestingly, the amount of apparent adsorption of DETPMP and dolomite is higher than calcite, although dolomite is less geochemically reactive, less reactive than calcite. So this is the conclusion of this part. So the amount of apparent adsorption of DETPMP and calcite is higher than on calcite, and dolomite is higher than on calcite, and the amount of apparent adsorption is increased as pH is increased. And now the answer, why? Why? Because we expected to get more adsorption on dolomite rather than calcite. The answer is here. So first we need to run compatibility test to look at the compatibility of scale inhibitors with CC water. At pH 4, as you can see, there is no changes in pH, which means that DETPMP is compatible with North Sea water at pH 4. However, at pH 6, after 100 ppm, the pH starts to decrease because of missing calcium and phosphorus from scale inhibitor. So DETPMP is incompatible with North Sea water at pH 6. After addition of carbonates into the system, the final pH increased to around pH 8 and 7 for the dolomite and the calcite respectively. And it is because of rock dissolution. So we have carbonate rock, and if it is dissolved in North Sea water, the pH starts to go up. Now, if you look at the final pH for DETPMP, dolomite, and calcite DETPMP, you can figure out the amount of final pH for dolomite DETPMP is higher than calcite. It reminds me that DETPMP in dolomite DETPMP system is higher dissociated compared to that of in calcite DETPMP. As a result, DETPMP in dolomite has more chelation sites to absorb calcium from surrounding, from around, and get precipitate. And this is the main result, the main reason why DETPMP has been absorbed mostly on dolomite rather than on calcite. Another indication in the solution is calcium. So as I mentioned before, once carbonate rocks are contacted with seawater or seawater with DETP-MP, it can be dissolved, and some calcium and magnesium, particularly in dolomite case, is generated in situ. So we expected to have the increased amount of normalized calcium for calcite in both cases. But as pH is lower at pH 4 and more acidic compared to pH 6, the rock dissolution is more significant than pH 4 compared at pH 6. That's why the normalized calcium for calcite is higher at pH 4 is higher than at DETP-MP calcite at pH 6. On the other hand, for dolomite, as you can see, after 100 ppm, the calcium is not generated by rock dissolution, which means that we have lack of calcium in dolomite DETP-MP system. In this system, calcium for precipitation, for complexation with DETP-MP, is compensated from North Sea water. That's why the normalized calcium for DETP-MP dolomite decreases below the baseline. On the other hand, for compatibility test, as I mentioned before, at pH 4, no changes in compatibility test. However, at pH 6, DETP-MP chelates some calcium and magnesium from North Sea water in the absence of carbonates, and then get precipitate, which confirms that the corresponding pH, final pH results and apparent absorption results. So as pH decreased, rock dissolution increased because of higher acidity of the solution, and then calcium generated in situ is also increased. So now I am going to present magnesium. So in both cases, calcite and dolomite, magnesium doesn't have that high affinity to be involved in chemical reaction with DETP-MP. However, in pH 4, in dolomite case, magnesium has increased because of rock dissolution, but for pH 6, rock dissolution is negligible, and the normalized magnesium is leveled off around 1. For compatibility test, in the absence of the carbonate, magnesium has been involved in chemical reaction with DETP-MP, but it is not as much as that amount of calcium which I have shown in the previous slide. So like the previous slide, as pH decreased, rock dissolution increased, and the amount of magnesium generated in situ only in dolomite increased. Now we need to look at the surface of the grains before and after scale inhibitor treatment in calcite and dolomite cases. So as you can see, in calcite and dolomite, we could detect some phosphorus around the calcite and dolomite grains, 3% and 6% for calcite and dolomite respectively. However, in bulk precipitation, we could detect a significant amount of the phosphorus in both cases, and this amount of phosphorus detected by EDX is higher at dolomite system compared to calcite system, which also confirms the corresponding apparent absorption of DETP-MP and dolomite and calcite. Okay, and it also confirms that the precipitation is formed as a separate phase. It doesn't adhere on the calcite or dolomite grades. Now, as a conclusion for this part, both absorption and precipitation region observed for DETP-MP carbonate precipitation, carbonate system, but precipitation is dominant in carbonate substrates. for DETPMP, the retention was greatest at high pH, as the scale inhibitor functional groups were more dissociated or available for complexation with divalent ions, and DETPMP retains more strongly on dolomite than calcite. And EDX detected phosphorus concentration are seen in the deposit where the coupled adsorption and precipitation has occurred, and the EDX levels are higher as precipitation or apparent adsorption increases. Now I'm going to present the PPCA result. PPCA is a polymeric scale inhibitor, which is also widely used in oil field applications. The test results are as follows, are as the same as I already presented for DETPMP. So the apparent adsorption results, again from 100, from 0 to 100 in both cases, the apparent adsorption mechanism is pure adsorption. However, once the concentration of scale inhibitor is increased, the apparent adsorption mechanism changes to precipitation. And so we can conclude it that PPCA on dolomite is adsorbed or is precipitated as the amount of PPCA on calcite. They are more or less the same. And it is completely different than what I have already shown you. Apparent adsorption for DETPMP as a phosphonate scale inhibitor is higher on dolomite compared to on calcite. And for PPCA, the apparent adsorption for pH4 is higher than for pH6, which is verse of DETPMP. In DETPMP, the pH, the apparent adsorption was higher at pH6 compared to pH4. Now we have to understand why these scale inhibitors behave differently. Okay? Now we need first to analyze pH. For compatibility tests, in both initial pH adjusted 4 and 6, no significant changes in pH, which means that PPCA is compatible with no CC water at both pH 4 and 6. However, after addition of the carbonates into the system, the amount of final pH is increased because of rock dissolution. And then the system is buffered due to the presence of the carbonates. And if you look at the final pH for dolomite and calcite, again, as I already shown you in DETPMP, the final pH for dolomite is higher than that of in calcite. Okay? So in the case of normalized calcium for pH 4 and pH 6, as pH 4 is more acidic, rock dissolution is more noticeable, more remarkable compared to pH 6, and that's why the amount of apparent normalized calcium is increased continuously in both cases, calcite and dolomite. And as we know, the amount of the content of the calcium in calcite is higher than in dolomite. That's why the normalized calcium in calcite is higher than in dolomite. But for pH 6, the amount of rock dissolution is negligible because the system is very close to neutralized system, and rock dissolution is negligible. That's why we don't have, sorry, increased amount of calcium in the system. For magnesium, for pH 4 and 6, no significant changes in the normalized magnesium, but we can conclude that as pH decreased, the rock dissolution is increased and the amount of magnesium generated in dolomite is higher. Okay. Now we need to look at the the bulk precipitate and the grains of calcite on dolomite by ESCM, EDEX, and particle size analysis. In this case, in PPCA, as the amount of phosphorus in the structure, in the chemical structure of PPCA is not that high to be recognized by EDEX, we had to change our analytical instrument to the particle size measurement. So we could visually see some bulk precipitate, but we didn't detect any phosphorus around, as due to the low content of the phosphorus in PPCA. In particle size analysis, we need to use two different types of lens to look at the big grains and the fine grains. In 300 millimeter lens, there is a good agreement for the big calcite grains. And when we change the type of the lens to the smallest one to look at the fine particles, for pure absorption region, we couldn't detect any peak. However, after the retention mechanism changes to couple absorption and precipitation, we could detect a peak, which confirms that couple absorption and precipitation is also occurring in PPCA carbonate system. As a conclusion for for PPCA carbonates, both absorption and precipitation region observed for PPCA. However, precipitation is dominant in carbonate substrate, as observed for DETP-MP carbonate system. Highest PPCA retention was observed at low pH for ore substrate due to the increase in divalent cations available from rock dissolution for scale inhibitor divalent cation precipitation. And PPCA retains about the same on calcite and dolomite, contrary to DETP-MP. To remind you, DETP-MP retains more on dolomite than on calcite, which is completely different than PPCA. And particle size analysis clearly shows fine precipitate in the couple absorption and precipitation region, which wasn't observed for pure absorption, and much larger carbonate grains can easily be distinguished by particle size analysis from the finer precipitate. Now, I'm going to show you some simple but very important mass balance calculation just for DETP-MP and carbonate systems. So what's the fundamental of mass balance calculation? We need to understand what's the destination of the calcium in the solution. So as I mentioned before, when the scale inhibitor contacts with the carbonate, it can be dissolved. I mean, the carbonate system is be dissolved by scale inhibitors, and some divalent cations, depends on the type of the carbonates, is generated, like calcium, magnesium, etc. So, initially, before we start the experiment, we have the 5 or 10 gram doesn't matter of the substrate of the carbonate in contact with North Sea water and DETP-MP, the scale inhibitor. So after putting in the oven and 24 hours, we take off the samples from the oven. In this system, some scale inhibitor has been absorbed on the substrate and some scale inhibitor has been precipitated out. So we have precipitation and some scale inhibitors absorbed on the surface. On the other hand, the initial concentration of calcium changes to the final, and DETP-MP concentration changes to final scale inhibitor concentration. If we write down mass balance for calcium in both systems, the total calcium in the first system is the calcium first in North Sea water, which is measurable by ICP, inductively coupled plasma method, and some calcium, which we have in the matrix of the substrate. On the other hand, after the experiment finishes, we have some calcium left in the supernatant, some calcium involved in precipitation, and some calcium which has been dissolved, which has been left in the chemical structure of the substrate. So according to the mass balance for those systems, and we assumed that the mass of the substrate before and after dissolution by scale inhibitor is more or less the same. Okay, because they are not that strong acid to dissolve significant amount of the substrate. That's why we assume we haven't, the amount of the substrate hasn't been changed significantly. So the calcium from rock dissolution equals the amount of the calcium involved in precipitation minus initial concentration of calcium in North Sea water and final calcium left in the supernatant multiply volume of scale inhibitor concentration. So on the other hand, the total calcium in precipitation and solution equals to the calcium left in the supernatant, which is measurable by ICP, and some calcium involved in precipitation. By substituting equation 2 with equation 1, we can conclude that the amount of calcium from rock dissolution equals to the total amount of calcium in precipitation, involved in precipitation and left in the supernatant minus calcium in North Sea water. Okay? Now the average calcium generated from carbonate dissolution results. I have calculated the average calcium generated by rock dissolution for both calcite and dolomite. As you can see in both systems, as pH is decreased, the amount of calcium generated by rock dissolution is increased. On the other hand, the amount of calcium generated by rock dissolution at calcite DET-PMP system higher than that of in dolomite and DET-PMP system. And it does make sense actually, because the content of the calcium in DET-PMP calcite is higher than that of in dolomite and DET-PMP. And then I plotted up the calcium in precipitation, how much calcium has been involved in precipitation, and how much calcium has been left in the supernatant for DET-PMP calcite system. As you can see, this is the blue one, the blue bar is the average calcium in the solution, and the orange one is the calcium in precipitation. As you can see in this amount of pH, the difference between average of calcium in precipitation and average calcium in solution is decreased as the amount of pH increased. Why? Because at pH 2, if you can see, we have calcium rock dissolution in the highest amount because the system is more acidic and most of the substrate is dissolved by scale inhibitor. That's why the amount of the average of calcium in the solution is higher than at pH 2 compared to two other pH values. However, this system can confirm that the more calcium in the solution left than that of in precipitation, it means that we have excess of calcium in the solution. So we have rock dissolution, and some part of calcium generated by rock dissolution is involved in chemical reaction with DETPMP. Some of them left. That's why we have excess of calcium in the system. But the story for dolomite is completely different. In dolomite, we have lack of calcium in the system. As you can see, the amount of calcium in precipitation is higher than the amount of calcium in the solution, because the content of calcium in dolomite system is less than the amount of calcium in the calcite. That's why we have lack of calcium, and this calcium is compensated mostly from North Sea water. As a conclusion from this part, the lower the solution pH, more rock dissolution, and as a result, more calcium generated in situ for two substrate. And for DETPMP calcite system, more calcium left in solution than more involved in complexation. And for DETPMP dolomite system, more calcium involved in precipitation than left in the solution. And for both DETPMP carbonate system, difference between calcium in the solution and calcium in precipitation reduces as pH increases. So as a summary of conclusion, the highest PPCA retention observed at low pH for all substrate due to increase in divalent cations from rock dissolution for scale inhibitor complexation with divalent cations, and DETPMP retention greatest at high pH, scale inhibitor functional groups more dissociated and more available for complexation with divalent cations. DETPMP retains higher or more on dolomite for PPCA in both system, calcite and dolomite are more or less the same. And EDX detected some phosphorus in final precipitate for couple adsorption precipitation region, and phosphorus levels higher as precipitation increases for DETPMP and carbonates. Regarding particle size analysis for PPCA carbonates, the final precipitate in the couple adsorption and precipitation region, which wasn't observed for pure adsorption, the lower the solution pH, the more rock dissolution and more calcium generated in situ for both substrate, and DETPMP calcite system, more calcium left in the solution than involved in complexation, which is completely different than for dolomite system. More calcium left in precipitation than left in the solution. And the difference between calcium in the solution and calcium involved in precipitation reduces as pH increases. And this is the all of publications that I have got during my PhD studies at Heriot-Watt University, the flow assurance and scale team. At the end, thank you very much for your attention. And I am hugely grateful for all industrial sponsors to support my PhD thesis financially. And I hugely appreciate my PhD supervisor, Professor Ken Sorby, Mike Singleton, Professor Eric Mackay, for supporting me during the PhD, and I'm quite happy to answer your questions. Thank you very much.
Thank you so much, Mr. Jarrahian, for providing such an informative presentation. I placed some of the questions that I received till now in your chat box, and the other audience also, they can ask the question in the chat box. I will transfer to Mr. Jarrahian for answering.
Okay.
Okay.
Could you please answer the question?
Did you receive it?
Yes, yes, I have received it. So why for the first one? Okay.
Yes.
The first one is why for scale inhibitors we need polyacids, and it is possible neutral substrate work as scale inhibitor.
Neutral substrate.
Neutral, sorry. So regarding your question. So generally, scale inhibitors are squeezed at lower pH because, as I mentioned before, if pH is increased, the scale inhibitor mostly, not all of them, mostly are incompatible with the injected water. So if we injected the scale inhibitor, in this case with higher pH, squeezed to the near wellbore, we get incompatibility issue and they don't work properly. That's why we use pH 4 and pH 2. On the other hand, we have to consider the materials which we are using for squeeze treatment, because pH 4, 2, they are acidic, and we have to use all instruments which are resistant against the acidic solution. And the second question is, what's the current challenges in scale inhibitors? So, good question. I can answer to your question like that. So, today I was presenting scale inhibitor squeeze treatment in carbonates. In industry, they haven't been convinced precipitation can increase the squeeze lifetime because of induced formation damage in some cases, right? So I can say that the scale inhibitor squeeze treatment in carbonate formation is one of the most important challenges in the oil industry, particularly in the Middle East, which we have a lot of loads of carbonate systems. And another challenge is environment. So those scale inhibitors which I presented today are not environmental friendly. So we need green scale inhibitors. On the other hand, we need to look at the chemical structure of the scale inhibitors. Most of green chemicals don't have a good retention. We have to optimize the retention properties of the scale inhibitor and the chemical structure, which is another challenge, very, very important challenge, particularly for production chemists, for chemists, to look at the scale inhibitors, which can be used in the future for oil and gas industry. And the third one, do we have scale inhibitors for all the scales? If not, why and how can we discover a new one? So I can say for this type of scale inhibitors which I presented today, they are mostly used, for instance, DETPMP in the Middle East and PPCA, and I haven't presented that one, but I have put it in one of my paper in SPE production, published in SPE production and operation, VSCO, which is a sulfonated copolymer, sulfonated polyvinyl acrylate copolymer, if I'm not wrong. This is mostly used in the North Sea, which is sulfate, particularly sulfate scales are very important to be controlled. And how we can discover a new one, as a chemist, I would say, if we have for instance, if we manufacture, if we use the previous chemical structure of scale inhibitors and do a reverse, for instance, synthesis of the scale inhibitors, we have to consider the functional groups because they are very, very important in terms of the chemical reaction with divalent cations. This is one of the most important way to discover the new one. And why we need, as I mentioned in the second question, we need green chemistry. We need to consider environment. That's why we need new scale inhibitors, particularly for the scales. And accept that for all scales, we can't use all scale inhibitors. Depends on the operational conditions, depends on the capability and ability of the scale inhibitors in terms of chelating the scales. We can use specific scale inhibitors for that. And can we certain scale inhibitor for different scales? What the criteria should be considered? So one of the most important criteria for the scale inhibitor, one is compatibility. The scale inhibitor should be compatible with any injected water first. And the second, the scale inhibitor should have a high and very good retention on the surface of the rock. And this is the second criteria. And the third criteria is to look at the dynamic of the scale inhibitor after you brought back the production well, to the well to production, sorry. In this case, we need to determine minimum inhibition concentration, or MIC, okay? By looking at the return curve. Unfortunately, during my PhD, I couldn't do that because of lack of time, but I strongly recommend, if someone is interested in this context, in this topic, to look at the dynamic absorption of scale inhibitors in carbonates. Because as I mentioned before, if we don't consider the scale inhibitor properties and mineralogies, whatever, in the squeeze treatment of the scale inhibitors into the carbonate reservoirs, we may induce a formation damage. So in this case, instead of remedying the problem, we have created another problem. That's why we have to look at pH, mineralogy, particularly in carbonates. Formation damage, to look at the permeability after and before scale inhibitor, compatibility tests, and retention mechanisms. And another question, in what conditions scale inhibitors are not effective and we can see the scales? So in what conditions scale inhibitors are not effective? So I can give you an example. Imagine that you have squeezed a scale inhibitor, but this scale inhibitor doesn't have a good retention properties. In this case, after the well is brought back to production, the all-off scale inhibitors is swept by the water stream coming from the reservoir, and they cannot prevent the scale formation. In this condition, the scale inhibitors are not effective. And also, if the scale inhibitors are not compatible with the injected water. So in this case, when you inject the scale inhibitors, squeeze scale inhibitors, sorry, these scale inhibitors get precipitate. And this is a malfunction actually for the scale inhibitors. So that's why we need to look at compatibility and retention to see in which circumstances, in which situation the scale inhibitors act effectively. Is it possible scale inhibitor decomposed as a phosphorus detected in EDX? I haven't looked at, to be honest with you, and I don't have any idea about it. Probably yes, probably not, but I have, this methodology has been repeated by some researchers, not only me, from our group. And I would say if it was a problem, I mean the scale inhibitor decomposition, they wouldn't run again and they wouldn't report in the literature. But to the best of my knowledge, I don't know. Please ask, okay, are you or your group working on green scale inhibitors too? In Priemer Oilfield Group, no, because we have recently to get some projects on scale inhibitors. But in the group where I have done my PhD, flow assurance and scale team, we have looked at phosphate ester scale inhibitor and sulfonated scale inhibitor. Both are green scale inhibitors. But the main challenge for green scale inhibitors is how to analyze them and how they can retain on the surface of rock. For instance, in VSCO case, we couldn't use ICP. We had to use spectrophotometer method. And you know, this is not as accurate as ICP. Recently, one of Finnish, I can't remember the name of company, has claimed that they have developed an analytical instrument to analyze the green scale inhibitors. But I would say it is expensive and it hasn't been developed for industry so far, to the best of my knowledge. And the procedure you use is applicable at water flooding too. I think, yes, it can be applicable at water flooding because this is the method that all companies like Champion X is squeeze and scale inhibitor during water flooding in most North Sea oil reservoirs. Is there any chemistry which can be considered green and with a good retention in rock simultaneously? I haven't presented VSCO. I can say it's a green chemistry, green scale inhibitor. It has a good retention, but it's not as good as, for instance, PPCA. It's not as good as polyhydric alcohol phosphate ester, for instance. But this is a big challenge. As I mentioned before, this is a big challenge. And particularly for chemists can develop a green chemistry which can have good retention and good thermal stability at the same time. Okay, but I have used just two green chemistries, phosphate ester and sulfonated polyacrylic copolymer, and both actually they gave me a good results. Is there any chemistry which can be considered green with good retention? Okay, I think I have done all questions. Is there any more question?
No, I didn't receive any other question. Okay, with this, as we are almost done with the time, once again, I would like to thank you, Mr. Jarrahian, for his very interesting presentation, and all of you for taking part in this event. Just for your information, a recorded version of today's webinar will be available in the APPIH social networks by end of today. Thank you very much and have a great time.
Thank you very much for the American Petroleum Professionals of Iranian Heritage for giving me the opportunity to present my work. And I really appreciate all of you for participating in my presentation. I wish all the best to all of you. Thank you very much.
Thank you.